So this illustrates some of the threats that we would have, and two of the core ones that we would see is when we have our electromagnetic side channel analysis. With this, the intruder would have an antennae that would be placed near the embedded device. Then when the CPU is operating, then the operations will give off electromagnetic waves, which can then be picked up through an oscilloscope. And then we can use what's called CPA, or correlation power analysis, or differential power analysis, along with a knowledge of the encryption method to be able to crack the encryption keys. Another way is that noise is created in the power supply through the CPU operations. We can then tap off the power supply and then feed that into our digital oscilloscope and listen to the noise that's created. And again, we can use that to be able to discover things like encryption keys as they're being used within the system. Another way that we can compromise the devices is to inject a hardware fault. So with some processors, if we cause glitches, we can slow down the clock, and we can possibly add in additional cycles into the computation. So for this, we can use an electromagnetic fault injector. So that's typically, again, with an antenna, but we create electromagnetic outputs to be able to compromise the circuit board. We can glitch the clock in some way, and we can also play with the voltage levels, because that can cause some of the chips to have some problems. One problem in the past that's happened, it happens with DRAM memory. With this, we can modify the bits around a memory area, and the charge will leak from those bits into our target. So even though we're not allowed access to the red bit here, we can influence that red bit by hammering the charge on the cells around it to make it a 0 or a 1. So this was a vulnerability that's been demonstrated within Rowhammer, and it's called hardware fault injection. We can obviously snoop on the data bus. If we're able to get a probe onto the chip and into the data bus, we could listen to the communications, and obviously we could even try and inject data into the data bus to cause the CPU to take incorrect data. There's also a method that we can use if we have a peripheral which is using direct memory access. It allows us to write into the memory area, into the embedded device. Then it's possible for us to inject different data into it. Bad storage from external devices, such as with a bad USB device, can also be used to compromise the device. And another threat that we can have is that we can look to modify the timing, or look at the differences in the data in the cache and in the main memory, so that we can actually compromise the CPU in some way. This was shown in Spectre and Meltdown as a particular problem, because the cache is doing a look ahead always to look at the data that's likely to be coming up. But if that data is modified in some way, then we may be taking it from the cache rather than from the main memory. Also, unverified firmware on our peripherals can cause a problem, and also it may be possible to be able to examine the data that's on the data bus between the device and the peripheral. The JTAG interface is obviously a problem area, because that's typically can be used to interrogate the device, and in some cases it can be used to reprogram the device too. So we need to make sure that many of the elements with the JTAG interface are disabled. So those are some of the attacks that we might have on our devices. Obviously, if we have an interface on our device then someone could break the pins or inject out-spec voltages onto that interface too. So there are many threats that we have when we're looking at the hardware of the device. So this shows an experiment here where someone put an antenna next door to a computer here, and they were able to listen to the communications from the laptop, in this case from next door. What we might see is something like this, and these are the operations of the AES encryption, such as mixed columns, shift rows, and so on. With this type of output, we can start to guess what the key is that's being used within the device without actually tampering with it at all, just by listening to the electromagnetic radiation from it. And this shows an RSA crack. With RSA, we're raising a message to the power of E, which involves an explanation. With this, we either double our values the way that the explanation is done, or we create a sum. We sum and double, or we sum. And we can see here, this is a timing attack, which allows us to see whenever we have possibly a 1, and a 0, 1, 0, 0, 1. So the timing attack allows us to be able to view how long it takes an operation to perform. As much as possible, a designer should try to obfuscate this by putting in fake cycles and to try to even out these timing problems. And just recently, an YubiKey was cracked, the version 5 YubiKey. And with this, they put a small probe above the chip and were able to listen to the radio wave emissions from the device and crack the ECDSA signature, and eventually to reveal the private key that was stored on the device.